Developable surfaces, we talk about those a lot. I think these are great. These cone circles. This is like a Naum Galbo sculpture. He's a constructivist. These are uh, um, uh, made very easily, but they are closed shapes, and so they are kind of helpful sometimes. So in order to make one of these, because they are rotationally continuous, this file, by the way, is uploaded. All you need to do is take some curves next to each other, draw two circles with 2 point, 1, 2, 2 point, 1, 2, rotate it up. Rotate it out. And then because they are rotationally continuous, Rhino is able to find the plane using the, if you use this circle and you click on the tangent tool, Rhino is able to insert a circle tangent to those. So you can insert a circle that way and insert a circle over there. And then you can trim those circles, put those circles with each other. Like so. Whenever I do tutorials, we always worry about the timing of these things. Sometimes there's little errors. Um, and then if you extrude those to the middle, it makes one of these cone circles. And you can pop out the middle with the sphere, and you can have different numbers of them and different degrees and angles of the continuity. So extruding those to the middle, I did this with 4, but I could have done it with 6 branches or 5 branches or 2 branches. And then if I put a sphere in the middle, I can pop out the center of the apex of the cone, which you can never build. You can never build the apex. And that object is the same as this object. Okay. So I think the cone circles are closed developable surfaces. Okay. Developable surfaces also, this person, Antoine Pevsner, who is Naum Gabo's brother, was the person that explored the tangent developables most in history. These are all developable. All of his sculptures are developable. Like that is developable. This is in Venice. I remember I was there for the Biennale. I stared at it for like 45 minutes. I thought it was a hype bar. It's not. It's just a developable surface. Okay. So it's the same thing, by the way, that my students made here, the same construction. So I will show you how that works, why it looks like this. I stressed about it for like 6 hours one time and figured it out. So it's made as follows. It's a helix around a curve, starting from a helix. So if you do the helix command, around curve, then you give it a radius and a number of turns. So I'm just going to give it 1 turn. And then if you extend the tangent of the helix, Mon showed you this, you can sweep one rail, the tangent along. Okay. I'll go faster. Wonderful. You can sweep one rail along the, you get that. The tangent developable helix. This is any curve swept along, any tangent curve swept along another curve can be unrolled. We'll talk about how to unroll them in a second. But what he does, okay, is he simply trims it in a funny way. So, like, if you look at this, there is a sort of a 45-degree box in here. It could be made like that, like between the two axes. And that box is extended. And then this thing is extended. And then they are, this is split with the box, like that. So it has these funny triangular ends. Okay, and then what's interesting, why I think it's interesting to look at this, okay, is that tangency, if you rotate a surface 180 degrees around one of its isocurves, it will always be tangent to itself. So like if I rotate this surface 180 degrees around its isocurve, it's always going to be completely continuous with itself. That's always the case. And if I mirror it also, it will also be tangent at that point. So there's a few axes of symmetry in here. So there's an axis of symmetry like from that to there, from the center point. So if I mark the center point like this, and then I draw the perpendicular plane, which I can find like that. There's a plane right here. There's a plane there. And then there's also a plane here. And then there's also the plane that is 90 degrees to this, like that. And if I mirror this surface about these planes, it will give me that, okay? Which is miraculously that. The same thing, okay? So these nested symmetric tangent developables, I think, are an interesting thing to explore. Why are they interesting? Because they want to flatten. They want to, and so you have to tension them together in order to get them to hold this shape. And then you can support things on them or do anything with them if you pull them together across the middle place. So it's like an interesting geometry to explore the dynamics of an arch with. And also they look like they're twisted and they're not. When you want to build these things, Iman was talking about how difficult it is to unroll them. The way to do it is you have to divide them into, you have to make a bunch of points. And then you have to take the isocurves. You can see how screwed up the geometry is right now. It's not behaving normally. If I take all these isocurves, and then I split this by those isocurves, a NURB surface is always four-sided. So it's always four-sided somewhere in space. I shouldn't have selected all these things. Okay. Um, if I untrim this, it'll turn into the original. If I shrink it, it will limit it to the area that it is selected by. So I can shrink all of those, and then I need to rebuild them as degree 3 surfaces with a bunch of points. And then I join them, and then I unroll them. It'll work most of the time. If it doesn't work, we have to triangulate them, which I can show you how to do as well. But that's how you do it. If you rebuild them and lose all the information, and shrink them down, it's not working. It will work, I promise. We'll do it. If it doesn't work, you talk to me and we'll make it work together. Okay? That's how you build them. They unroll to be basically just circles in plan. So like I think this one will unroll. There you go. It looks like that. So there's a part that's not unrolling correctly, which is this part. The last bit. Yeah, I can tell because I know these shapes. That looks wrong. So like if when it looks wrong, what we do is we divide each of these into 2 triangles, and then we unroll it, and then we're not panelizing it. So it doesn't matter that we unroll it as triangles. All we're looking for is the correct shape to cut out of a single sheet, and then we can unroll it up. If we were panelizing it, it would matter that it was triangles. We wouldn't want it to be triangles because we're trying to build a flat plane. But here, all we care about is the overall shape, making sure it's the right area and isn't developable so that we can roll it up. Okay? All right. There's another developable thing I want to go through with you, but I want to skip ahead for a second and move on to more complicated things. The other developable that I want to go through with you on is these, which are self-intersecting developable surfaces, which I will go through in a minute. Okay. Ruled surfaces is the next level up. Developable surfaces are ruled surfaces. Ruled surfaces are twisted surfaces where the ruling lines aren't parallel within the sheet. Not parallel, but like in a developable surface, each successive ruling line is at the same tilt in space relative to the original curve. It's hard to visualize, but like they're sort of at the same angle relative to the original curve, so it unrolls flat. In a twisted surface, they're all over the place relative to the curve. So that's a ruled surface. And when you loft, if you check the straight sections, it will constrain it to be straight ruled surface with straight line isocurves. And a special case of ruled surfaces is what's called a conoid. And a conoid is just a ruled surface with a single straight line somewhere in it where all the isocurves pass through a single straight line. This is what's called Borini's conoid. Okay, it's this particular special conoid that happens to be the roof of Ronchamp is Borini's conoid. That is made just by lofting a circle, straight line, like so. I think these are exciting, by the way, because even though they look boring, in the aggregate, they are somewhat interesting. If you mirror them and rotate them, you can make things like this. Okay, those are half rotated and mirrored against each other. So I think the conoid is an interesting thing because it has some sort of a controlled shape, but it has curvature that isn't ideal. And another interesting conoid is this one. This is called Plüker's conoid. Has a tilted circle within it. So you can make one of those by going 2 points like that, splitting this, and then lofting each half. To the axis like that. So I think if you clip the ends, they look like this. It's exciting because it has some architectural interesting topologies. It's got throughways and like possibility of shooting a core through it or something like that. And also maybe floor plates in here and a canopy on the underside. I don't know. They have an unusual topology. Okay. So conoids. I also think that the sweeps, just the general sort of tangent planey surface, if you make a closed composite out of them, could be interesting. As well as somebody in here was doing the conicals, the sweeps between two circles. I think this is an interesting one. The cyclide is nice, which is basically a torus, an asymmetrical torus. And you can make that by essentially offsetting the center of a torus like this, and then drawing the profiles. So if I do this 2-point vertical, and then I can just sweep two rails. And mirror it. And you get this asymmetrical torus. Really, any of the shapes you explored with Amon are okay, but they should be closed and definitive. So this particular sweep two rail needs another one. It needs something on the underside or two sides to make a closed form. This one doesn't. You could also make a composite of these, two of them together. But the complexity should remain in the realm of 2 or 3 surfaces intersected, because I want you to build them like this, which if you make crazy composites is going to be overwhelming to deal with the joints. Okay, so like 2 surfaces, like 2 of those would be the maximum. Or one sort of interesting sweep or conical that forms a closed shape would be how you want to start. Yes?
Give me examples of the strip discretization for like a spherical or an ellipsoid surface or something that would be divided radially.
Yeah. So a sphere just discretizes normally. Like I can show you that actually. So if you just take a sphere, okay, and you I think I need to split it in half, or it won't work. You take a sphere, you split it, and you extract like the isotopes. Like that. That's planar. So if I loft between these two, this right here is a plane. So in the limit, that as a ruled surface with straight sections is developable. That's the developable surface. So you can discretize a sphere with a series of developables radially. And you can do the same with a torus. Any quad panelizable surface, surface of revolution or surface of translation can be discretized directly from the isocurves. You don't need the principal curvature thing, which is fine. I'm okay with that. You don't have to use the principal curvature thing, but we want the shapes to be questions in terms of the thickness paradigms that I was thinking about originally. By the way, I have something here which I will show you. if in the previous thing, there's this quad panelization script. And if you take these isocurves and you put them and you do the you order them first. You have to go tools, Rhino script, load, order them, order these. And then if you put the V's in there and the U's in there, it'll just do it for you. Okay, so this little thing in this quad panelization script takes ordered U and V isocurves and pops panels on them. And it'll do it also with the principal curvature isocurve. So if you have two ordered strips of principal curvature lines, it will just produce the planes. Although we're not producing planes, we're producing the developable surfaces. So it's not quite as useful. You need millions of isocurves. You can just loft the way I was doing a second ago. Okay, does that make sense? Cool. Okay. The next thing I want to look at is I want to skip ahead here. Non-orientable surfaces, Klein bottles.